Hello students and welcome to Unit 7 Part 2 Lesson 1. In this lesson we are going to learn another strategy for solving systems of linear equations by using substitution. Our essential questions for today are 1. What is a system of linear equations? 2. Describe the solutions to a system of linear equations. You already know how to do this. This means describe them as having one solution, which is an ordered pair, as having infinitely many solutions, meaning that all the ordered pairs on the given line will make the equations true, or as having no solution, meaning no ordered pairs could ever make that system of linear equations true. And third, how can we use substitution to determine that solution? We already know how to guess and check, and how to use graphing as a tool to determine a solution. Substitution will be another tool in our belt of strategies. So as you can see, I have this picture of a basketball team playing. How do you think solving systems using substitution relates to basketball? Well, in basketball, when one player exchanges places with another, that is called substitution. When a team makes a substitution, the coach replaces one player with another. When solving systems using substitution, we will replace one variable with an equivalent expression. So here are our steps for solving a system of equations by substitution. First, solve an equation for one variable. Pick the easier equation, and I'll show you what this means. The goal is to get y equals a number, x equals an expression, a equals an expression, etc. It does not matter what variable we isolate, we just need to get one of them isolated. And sometimes our equation will already have step 1 done for us if we pick the easiest equation. Step 2 would be to put the equation solved in step 1 into the other equation. It's very important for you to make sure that you are substituting from one of the equations into the other equation. Third, solve the equation. It will now be a one variable equation that will allow you to get the variable by itself. Afterwards, plug back in to find the other variable. In other words, substitute a number that you found for the first variable back in to solve for the other. And last, check your solution. Substitute your ordered pair into both equations to make sure that it is true. These steps will make more sense as we solve a problem together. So let's look at this set of this system of equations. We have two equations. I know they're both linear because this one's in standard form. This one is a variation of y equals x. We want to get one variable all alone. Remember, that was step 1. If you look at the second equation, y is already isolated. Y has exactly the same value as 3 plus x. So whatever this number is here, it's the same as 3 plus x. So step 1 is already complete. We have a variable all alone. Y is equal to 3 plus x. So anywhere that I see a y, I can write 3 plus x instead because it's the same value. Now step 2, I'm going to substitute this equivalent value, 3 plus x, into the other equation where I see y. So here's our other equation. X plus y equals 5. Now, instead of writing y, what can I write? Well, I can write 3 plus x because that's the same value. Now, since this is positive y, I don't need to use parentheses, but if this was a subtract sign, I would need to use parentheses because then it would be the distributive property. So I'm going to put 3 plus x here instead of y. So I have x from the original equation plus y, which is 3 plus x, is equal to 5. Now, I've transitioned from a literal equation with two variables to a one variable equation because now I have just x's in my equation. This is a one variable equation with like terms on the same side, so x plus x makes 2x, so I have 2x plus 3 equals 5. This is a two-step equation. Subtract my constant to make 0. So I have 2x is equal to 2. Divide each side by 2 because I'm at a one step. 2 divided by 2 is 1. 1x is just x. And 2 divided by 2 is 1. So now I know that the solution to my equation has an x value of 1. So in this part, this was step 3. I solved the one-step equation to figure out the value of one of the variables. Now I know that x is equal to 1. Since I know x is equal to 1, I can substitute it back in to one of my equations, and it does not matter which one, but this one's going to be easier because y is already isolated. So I can substitute 1 back into the equation, and now I have y equals 3 plus 1, or y equals 4. So this was step 4. I solved for the other variable. Now I know my ordered pair. My ordered pair is x is 1, y is 4. This is the ordered pair that will make both of these equations true. And I can check my answer. 1 plus 4 equals 5. 4 equals 3 plus 1. Both of them make it true. So this system has one solution, and that's the ordered pair 1, 4. Okay. Now let's try another example. Remember, step 1 is to get one of the variables all alone. It does not matter which variable you choose. In this case, I would choose to get x all alone because this is already positive 1x. X is almost alone already. So this is step 1. My goal is to get x equals an expression. So I'm going to start with this equation, 3y plus x equals 7. I'm going to take away 3y from each side. I get x equals negative 3y plus 7. Now I know that x has exactly the same value as negative 3 times y plus 7. So anywhere I see an x, I can write this expression instead. Now step 2, I need to take this equivalent expression and substitute it into the other equation, which is this one, 4x. So this equation says 4x minus 2y equals 0. So instead of writing x, I can write negative 3y plus 7. Now, do you see how this is 4 times x? I'm going to have to use parentheses to show 4 times this expression. So 4 times negative 3y plus 7 minus 2y, because that was part of the original equation, equals 0. Now I'm at a one variable equation. This equation needs some simplifying done. The first part of simplifying is to use a distributive property. So 4 times negative 3y makes negative 12y. 4 times positive 7 makes positive 28. Bring down minus 2y and equals 0. Now we're more simplified because we do not have the distributive property, but we still have like terms on the same side. So negative 12y and negative 2y make negative 14y. So I have negative 14y plus 28, just bringing that plus 28 down, equals 0. Now I'm at a two-step equation. Take away 28 from each side. I have negative 14y equals negative 28. Divide each side by negative 14, which is 1y or y. What we do to one side, we do to the other. Negative 28 divided by negative 14 makes positive 2. So now we know half of our solution because we've completed step 3, solving for one of the variables. Now that we know that variable, we know y equals 2, we can substitute y equals 2 back into one of the original equations to figure out what x is. Again, I'm going to choose the first equation because I already know that x is 1x, and that'll save me some work. So I have 3 times y plus x equals 7. Now I know that y is 2, so I'm going to substitute that in there. So 3 times 2 plus x equals 7. So 6 plus x equals 7. Subtract 6, subtract 6. So x equals 7 minus 6, which is 1. Now you have to be careful here because remember, we solved for y first, but in our ordered pair, x goes first. So our ordered pair is 1, 2. This is the one and only ordered pair that will make both of these equations true, and you can check it. 3 times y, 3 times 2 is 6, plus 1 more makes 7. 4 times 1 is 4, minus 2 times 2 is 4, 4 minus 4 is 0. So this ordered pair indeed makes both of these equations and the system true. Let's look at this third system. I like this system because step 1 is already done for us. X is isolated. So our first step is to get a variable alone, which we already did. We say x is equal to 3 minus y. So anywhere that I see an x, I can write 3 minus y instead. So I'm going to take the second equation, which is x plus y equals 7, and I'm going to substitute equivalent values. See how it has an x? Well, I know that x is the same as 3 minus y. So instead of writing x, I'm going to write 3 minus y. So 3 minus y plus y equals 7. Now we have a one variable equation. This was step 2. We substituted in. Now step 3, we're going to solve it for y. So we have negative y and plus y. If you owe y and you have y, that makes 0. So I have 3 equals 7. Now I've solved this. What happened? I don't have a variable anymore. I have a false statement. Now what do you think is true about a solution if it has a false statement? If there's a false statement, then there is no solution. There is no solution because these two lines are parallel. So whenever the result is false, the answer is no solutions. There is no ordered pair that could ever make this system true. Let's solve this fourth example. Our first step is to get y all alone. I'm going to choose the first equation because y is almost alone already. I'll take away 2x from each side. I get y equals negative 2x plus 4. Now I know that y has exactly the same value as negative 2x plus 4. I'll take the second equation, which is 4x plus 2y equals 8, and substitute in for y, which is step 2. So I have 4x plus 2 times negative 2x plus 4 equals 8. I'll distribute. 2 times negative 2x is negative 4x. 2 times positive 4 is 8. Bring down the rest of my equation. 4x minus 4x makes 0, and I'm left with 8 equals 8, which is a true statement, meaning there will be infinitely many solutions.